Welcome to today's Engineering.com webcast. The format of today's webcast will be a presentation followed by a question and answer session. We encourage you to ask questions throughout today's presentation by typing in the Submit a Question box on the right-hand side of the webcast player. Should you require technical support at any point during the event, please click on the Contact Support icon at the bottom of the webcast player. A reminder, this webcast is being recorded today, May 28, 2013, and a recorded version will be available shortly after. I would now like to turn you over to your host, Mike Paladin, for today's presentation. Please go ahead.
Thank you. Thanks for joining our webcast. This is the first of a three-part series on how to overcome common FEA roadblocks. Today's session is on leveraging your existing CAD data. I wanted to point out that there's a few resources on your page there. There are three case studies from FEMAP that you can download and look at. We'll be talking about a couple of those in a little bit of detail today. Also, as it was mentioned, there is a Q&A session, so enter your questions anytime during the session today, and we'll get to those toward the end of the session. I want to hand it over to our main speaker, is Al Robertson from Siemens. He'll also be joined by Chip Fricke for our Q&A session later. So let me turn it over to you, Al.
Okay, thanks very much, Mike. Welcome, everybody, to this webinar series. As Mike mentioned, this is the first of three webinars that we have, which will outline common FEA roadblocks on the path from creating a finite element model right through to looking at some results. So the subject of today's webinar is leveraging your existing CAD data. And we're going to take a close look at how we can access CAD data and turn that into a finite element model. As I mentioned, it's one of three. The second one is in a month's time. This is we'll be focusing on creating an FE model from CAD data and creating a model that is actually useful for analysis. So we'll be focusing on the meshing stage at that stage. And the third one at the end of July, we'll be taking a look at making sense of analysis results. So in terms of an agenda for this afternoon's webinar, I'll start off by looking at why we use simulation tools and very quickly review the business needs for improving product design. Then we'll go and look at some of the typical roadblocks that people encounter when they try and access CAD data, and when they try to clean it up, and further on to actually idealize it. And we'll look at the roadblocks themselves, review some considerations about the approach taken, and also review a solution as to how you can get beyond those roadblocks. First of all, just by means of an introduction, just a couple of slides on the meaning of simulation, why people adopt a simulation process. And first and foremost is the ability to perform virtual testing. That is, perform testing of a design actually on a computer rather than physically manufacturing a prototype and seeing if the actual hardware runs. So by virtual testing, we actually reduce the need to perform physical testing, maybe not completely, obviously, but certainly in terms of reducing the number of prototypes, that's important, as it seriously reduces cost, increases time to market, and generally produces a much faster return on investment. Using virtual testing instead of physical testing, here we see a kind of linear process from concept through design to validation and finally production once the design has been validated. And in general, without simulation, by far the most longest and most expensive part of the whole process is the validation stage. By introducing simulation into the whole process, we can essentially reduce the physical validation stage and in terms of both time and money. But however, there is of course an effect by introducing FEA at the design stage. Of course, it's going to lengthen the design stage to some extent. But certainly overall, there's significant benefits to be had, both in terms of reducing time taken to validate and complete a design, and also the cost of doing so as well. So that's one of the main reasons for introducing simulation into the design process. Another one is failure analysis, and this allows us to improve product performance by investigating perhaps some failures that have occurred in the field and fixing them basically, or maybe even doing this before we actually get to the production stage, where we can actually improve reliability and reduce costly recalls. And this is all brought about through the ability of simulating the actual design on the computer before actually going to manufacturing or even testing stage. Another reason to introduce simulation is to optimize the design. And here you might take an existing design or even a design from scratch and introduce simulation to investigate ways of perhaps reducing weight and material to make the design both cheaper to produce and more efficient in terms of how it uses the material that the design is composed of. It's also a possibility at this stage to swap out expensive materials for cheaper substitutes and investigate those again. And this can all be done virtually to see if we can shave some cost of the design by using some cheaper materials. And another reason for using simulation tools is to perform trade-off studies. And this in itself helps innovation as well. So at the stage of putting a design together, it's possible to just go into the using simulation, just evaluate different designs just to see, well, what happens if I produce this kind of shape rather than that shape. And you can see just by evaluating all of this on a computer, you can very quickly get some insight into the way the particular design is going to work under different configurations. And that helps to promote innovation as well as giving a much more of an insight into the way the design is working. Okay, so the reasons for introducing simulation into the design process. The next couple of slides, we'll be looking at some of the main business reasons that are driving people to using simulation. And these all come from the source, a survey actually performed by the Aberdeen Group. This is a group that's dedicated to market analysis, industry analysis. And on this slide, they've identified from the survey that they conducted the top business pressures that are driving product design improvements. And here we see, right at the top there, customer demand for lower cost products. So right there's a requirement from the customers to have cheaper, less expensive products to buy. Shortened product development schedules, so there's a time aspect coming in there. We need to constantly reduce the development schedules, design for the design process. A couple of competitive pressures coming in, one to differentiate with better quality and reliability. So again, a classic use of simulation for that. And the second one, which is the bottom bullet there on the slide, is to differentiate it with smarter, more feature-rich products. And then the fourth bullet point, the one I've just mentioned, in fact, the need for greater innovation for new market opportunities. So clearly, simulation here has an impact on all of these points. The next slide is what's driving top product design, or what are the top product design challenges. And here we see problems and errors that are found too late, so that holds up the design process. The need to make trade-offs for cost, performance, and quality. Frequency of design changes. So these things are changing all the time, and the ability to adapt and respond to that quickly enough to maintain delivery targets is important. Predicting product behavior in a real-world environment, classic CAE use there, and some lack of technical expertise comes in as one of the design challenges as well. So the top objectives for improving product design, at the top here we see a decrease in length of development time, improvement of product quality coming in, increase in profit margins, and lowering of product costs. So all of the classic things that we strive to improve: reducing time, improving quality, making more money out of the whole process, and lowering costs. And best-in-class strategies to improve product design. Analyzing product behavior earlier comes in at the top there. Implementing a get-it-right first-time strategy, and this is really getting back to the very first point I made about use of simulation for virtual prototyping. While you might not be able to get rid of actual prototyping, physical prototyping completely, it might be possible to get the design to such a stage where you're confident enough that when you build the first prototype, it'll pass first time. Promotion of collaboration between analysts and designers, evaluating more design iterations in the concept design stage. So again, need for speed is paramount with that. And defining best practices for assessing product behavior, and CAE clearly can play a role there. Okay, so in terms of just taking an overview of the process, the simulation process, in general, we can go back and start from a CAD model. That's what we generally try to do. We can try and leverage the CAD data if possible. If not, it's possible to create from scratch, and that might be something we'd have to do at the concept stage anyway. But anyway, getting a model, turning it into a finite element model, that's really part of the process we'll be focusing on today, looking at some of the roadblocks on that path in this particular webinar. Once you have the CAD model imported into the simulation environment, then the task is then to convert that into a CAE model. That's going to be the subject of the next webinar next month. Then once the CAE model is built, it's sent off to a solver that performs all the number crunching, produces the solution, and the results can be read back into the simulation environment, and that'll be the subject of the third webinar at the end of July. So that's the whole process. We're only focusing on a small part of it, the initial part of it in this webinar. So we have a road to follow. We want to go from the CAD model to the FE model, and here we'll take a look at some of the typical roadblocks that people encounter in doing that. First of all, getting access to CAD data. That is quite problematic, or can be quite problematic. If you can't get hold of the CAD data, you can't take advantage of the fact that the CAD model is there and can be used and turned into a simulation model. So that's going to add time to the whole design process, the whole simulation process. Okay, supposing you have access to CAD data and you can import it, the next stage to get past is to actually be able to use it. And quite often there are quite a few problems just inherent in the CAD data itself. And being able to get past those and create an FEA model out of the CAD data is another common obstacle that can be encountered. Okay, so you might have read the CAD model in, and it's a good model, so it's very usable. Quite often, that's not always enough. You might need to actually depart from the CAD data to produce a CAE model that is usable for perhaps more advanced types of analysis. And being able to idealize geometry becomes quite important. So that's the third thing we'll take a look at. Okay, so we've identified the roadblocks that we're going to be looking at. This slide here introduces the solution that we'll be considering, which is FEMAP. And FEMAP is a standalone FEA pre- and post-processor. We state that it is standalone in that it can interoperate with just about any CAD system out there. It also can work with just about any or all the major commercial solvers that are out there. So in that sense, it's standalone. It's a high-performance modeling environment. It has very tight integration with NX Nastran, as well as being able to deal with all of the major commercial solvers that are, as I just said. It's also a Windows native application, and as such has a lot of intuitive processes and workflows, and can be easy to use and learn, which is important. So that's what we'll be looking at to overcome the roadblocks that we encounter on the way from bringing in CAD data to creating an FEA model. So let's look at the first one, accessing CAD data. Some considerations, the CAD model, as I mentioned, already exists, perhaps, and being able to leverage it and use it for simulation can actually save an awful lot of time. It just means that you don't have to go back to the beginning and create the model from scratch. It may be that you work in a multi-CAD environment, and you can see from a quote there from the Aberdeen group that 82% of companies have to use 3 or more CAD systems. So it's very important to have the ability to access CAD data from various different sources. I mentioned before, it may be the case that you need to create the geometry from scratch anyway, and FEMAP can do that if you're at the very early stage of the process. But certainly, if a CAD model is available, then it's obviously a real advantage to be able to take advantage of it and create the FEA model. So typical challenges that you can encounter as far as the CAD system itself is concerned. There may be limited support for CAD data types or formats, limited access to the CAD systems themselves, or perhaps even to the required version of a CAD system might not be supported yet. The latest versions support for the latest versions can come more slowly than you'd like. It may be that you can have access to a particular CAD system, but you can't get all of the geometry types across. So you may be able to bring in surfaces, but not solids. So these are all typical hindrances that can be encountered when trying to access CAD data. When faced with things like this, users have to resort to another method of data transfer, or even rebuilding the geometry from scratch. So the resulting costs then, missing geometry that has to be recreated, that's going to be very time-consuming. Having to find an alternative way to transfer data, again, time-consuming, or it might not even be possible at all. And all of these roadblocks will tend, of course, to lengthen the design and FEA part of the whole process, and may push you past delivery deadlines, which obviously you want to avoid if at all possible. Okay, so in terms of a solution for this, then we can talk about FEMAP, and FEMAP supports all major CAD systems and data types, and can offer reliable CAD import from a wide variety of sources. And you can leverage the existing design model from your 3D CAD system or systems if you have to deal with more than one, which precludes the need to recreate any geometry from scratch, which obviously saves a lot of time. Employing more than one modeling system in a multi-CAD environment, with FEMAP, you only need the one modeling system. So the ability to access CAD from multi-CAD systems, you can bring it all into one single modeling system, and that can save a lot of time and problems as well. Both being, FEMAP has a special relationship with Solid Edge. It has this interoperability capability with Solid Edge, which means that the data can be passed from one to the other, and updates if the model is updated in the CAD system, then the users in the FEA system can be notified of that. So have this relationship there. Okay, so just take a look at a case study at this stage, and this is a company, NoSim, who needed to acquire a CAE tool that could interface with multiple CAD packages that were used by their customers. And the key to their success was to select FEMAP, the Windows native software with this multi-CAD access capability. And that allowed them to automate the entire CAE process from simulation model generation through to analysis and final reporting. And that in turn actually reduced the finite element modeling time right down and ensured earlier design validation. It also allowed them to reduce prototyping costs as well. So it's some significant benefits that came from adopting FEMAP as the CAE solution there for NoSim. Okay, well at this stage, let's change gears a little bit and look at a demonstration. And this is a demonstration that will show CAD imports and analysis in FEMAP from Solid Edge, import from Solid Edge. Then we'll take a look at performing some refinements in the CAD system, and then pushing it back out to FEMAP from Solid Edge to perform another set of analysis and results.
FEMAP supports the import of multiple CAD formats, including the direct import of Solid Edge part and assembly files. In addition, FEMAP can import standard industry CAD formats such as ASYS, DXF, IGES, Parasolid, and STEP files. The Solid Edge material properties have been automatically assigned to the corresponding solid bodies in FEMAP, as shown in the Entity Editor pane. Bearing loads are applied to the two wheels, and constraints are applied to the base and side plates of the trolley. FEMAP is used to automatically detect and create assembly connections. Once a mesh is applied, a linear static analysis is run, and the results show that the stresses are well within the allowable for the materials used. This analysis also shows that the material thickness for the base and side plates can be lowered, allowing for lower production costs. The Solid Edge assembly is being modified to thin the thickness of the base and the side plates using synchronous technology. In this case, the design engineer is pushing the updated Solid Edge assembly into the FEMAP model file. The FEMAP dialog box indicates that geometry updates are available for this model. The Geometry Replacement Options dialog box offers control over updates, including mesh sizing and material updates. Loads, constraints, and assembly connections are maintained, so the only changes needed are to remesh and reanalyze the model. The analysis of the updated model confirms that the design changes maintain acceptable stress levels while reducing the cost of materials and production.
Okay, so let's move on to the next roadblock that we identified, and this is actually cleaning up the data once we can get access to it. So the task really here is to tidy up the geometry for simulation model creation, and a couple of considerations. The CAD geometry can contain much more detail than is really needed for simulation, for the purposes of simulation. So things like generally small details, things like small holes, fillets, chamfers, they all, if left in the model, will actually lead the mesher to create small elements to capture that detail. So if it's not really required for the purposes of simulation, that data has to be removed from the model. Another point about the CAD model, it can actually contain bad geometry. I mean, it's for the purposes of CAD, the model isn't being put together with simulation in mind. So there could be problematic pieces of geometry, things like short edges, sliver surfaces, if left in there, again, will lead the mesh generator to create very small elements to try and capture the small edges and that small detail. Or indeed, if the geometry is bad, it can create bad elements, which will lead to poor results. So a couple of things that we have to consider. So typical challenges then, when we're looking at using a CAD model that we've read in, we need to defeature and remove this unnecessary detail without oversimplifying the model. And this is a caveat here that some tools, they do this very well. They're very rigorous about it. They see small details and they will remove that small detail without performing all the really necessary checks. For example, there could be a small edge inside the model which is loaded. So that loading may be actually essential and needed for the simulation. So if it's on a small feature which is just removed, then the load disappears and we've lost data. So it's important that the system identifies or can identify the small details which do have this additional data and leave them alone. Locating and cleaning up bad geometry from the CAD model is really required to simulate FE model creation later on. So these are things that we have to overcome. So the challenge is then defeaturing and removing unnecessary detail without oversimplification, and really the resulting costs then, the creation of, it's possible if we don't get rid of this small data or this bad data, we'll create large FE models that contain too much detail, and they become time-consuming to run. And also, you have some consideration about the amount of data that's produced post-processing as well. You have a big model, is going to produce a lot of results data, so that needs to be a consideration as well. Bad geometry will generally lead to creation of bad elements, which can be detrimental to the mesh creation. Again, producing large models or even models which contain bad elements, which just quite simply give bad results. So we look at what FEMAP can offer. FEMAP does have automated methods of cleaning up the model. And it will remove detail without actually losing data. So it does, go through all of the checks to make sure that it's not removing data which is associated with other modeling data that I mentioned before. It also has a meshing toolbox which can be used interactively, and this has a lot of very important aspects to it. First of all, a locator. So you can easily locate problematic geometry like short edges or sliver surfaces. And it has some other tools which can fix up geometry. For example, if you have multiple curves around an edge of a surface, it can move all those together to form one curve. Or if you have multiple surfaces which are going to produce small meshes in particular areas, you can actually merge those surfaces together to produce a better model for meshing, essentially. So the interactive meshing toolbox is very powerful inside FEMAP. Some other things that you can do as well, again, from the preparation of a geometry standpoint, you can split surfaces up so that they better correlate with surrounding surfaces, which will produce a better mesh. It has an offset curve facility, so you can put a band around an area you think is going to contain high stresses. For example, around a typical stress razor like a hole, you can put better surfaces around there, which will create a much better, finer mesh with elements, well-shaped elements that are small enough to capture the high stress gradients typically you'd find in these problematic areas. So all of these tools, as well as the ability to remove the small detail from the model quickly and easily, are all important aspects. Okay, so let's go and take a look at another demo, this time looking at model cleanup, and we'll see how this looks in FEMAP.
A quick example of using some of the geometry cleanup tools in FEMAP to make a better mesh. I'll bring in here a piece of sample parasolid geometry. and this one's actually in millimeters, so it gets scaled up a little bit. The first thing I always do when I want to find the problems of my model, I'm going to turn off some of the extra edge information here, is use our locator. And what I want to do is find sliver surfaces. And I know this part's actually about the mesh size. Later on it's going to be a little bit bigger, so let's look for anything that will fit within a 1 millimeter circle, and there's 2 slivers in this model. The first thing we'll do here is get rid of them actually permanently by cleaning up the parasolid geometry. So we're going to go into feature removal. I'm going to say surfaces, and this is just removing regular fillets and chamfers and things. We're actually going to aggressively squish this right out of the model. So I'm going to look at the first one, second one, zoom in here, and just go pick them. And he's going to get pulled out of the model. Go find the other guy, pick them. And let's see what else we got here. Let's make sure we don't have any short edges in the model. So go back to the locator, go to curves, and let's see what we got here. There's 2 curves that are pretty short, and let's see where these are at. It zooms in. Oh, looks like we got another little ledge in here. This little flag-shaped surface. A couple of ways we can get rid of him. There's a split point to edge, which actually burns a little split right there. So now I've got a separate surface, and then I could jump right into feature removal and get rid of him. And let's go see what we got. Looks like the exact same thing on the other side. Yeah, there it is. Let's go ahead and do the same thing there. Basically created one extra little face there. Then I'm going to remove it. And you can see there parasolid geometry actually gets permanently updated. So now we've got good geometry. We'll just, let me bring up the meshing toolbar, and we'll just say mesh solid. Pick a material. Pick the mesh density automatically. Feed it through. Surface is meshed. It's going into the tetramesher. Loading. It's done. Now it's adding the mid-side nodes, hooking everything up to the surfaces for geometry-based loads. Let's turn everything off. And there, we got a nice mesh. Let's do the same thing without doing the permanent geometry cleanup. Let's actually use some of the virtual topology geometry in FEMAP to do the same thing. So what I'll do is create a new model, bring in that same piece of geometry, and I don't think we'll even need to use the locator. We kind of know where everything's at right now. Let's zoom in here and I'll show you what we can do. We do have this little sliver face right next to another face. So we do have a combined composite surface. They just pick a curve, and FEMAP actually just connects the 2 surfaces together. So we do the same thing there. Same end effect as what we did before. Do the same thing over there. And now we basically just combine those 2 surfaces. And then we also want to do the same thing with that little undercut in this edge here. So we'll basically just pick him, and that combines all that into one surface. And we can even run that right over here to the other side. And now that's all treated as one surface, kind of pulling that little ledge off. So I'll zoom back now, turn off the picking there. And I think all we have to do is just mesh them. So we'll pick the part, pick the same material again, say OK, and fire it through. And it's meshing. It's loading up the tetramesher. It's done tet meshing. It's getting the mid-side nodes in there. And here's our mesh. Looks good. Let me just turn everything off and turn just the mesh back on, just to verify it did what we thought it was going to do. Let's go down here and look up underneath this edge. So I'm going to set the view center right at that node right there, and then rotate up, and we see that underneath there, that little tiny sliver edge was taken out. We've got a nice mesh all the way up underneath.
Okay, let's move on and take a look at the third roadblock that we encountered, and that's to take a look at some geometry idealization tools. And here, the task we're faced with is really to idealize the geometry to create an accurate and efficient simulation model for the situation where we need to kind of depart from the solid CAD geometry. And some considerations then, if you look at the chart there, it's model size versus the time for solution. And this is really pertinent to a lot of solvers, but NX Nastran is mentioned in the slide here. And it offers two types of solver, the iterative and one which is, the iterative solver, which really is able to model, analyze very large models quite efficiently, but really doesn't lend itself to more advanced types of analysis like dynamic response or nonlinear. So we have to resort to using the standard solver, which of course can't analyze models of such a great size. So when we're considering taking a model and taking it into more advanced types of analysis, this has to be a consideration, and that really means we have to look at a much more efficient way of representing the design model. And there are various techniques available for us to do that. Some modeling techniques which involve geometry idealization can be used very effectively to reduce model size without having any impact on accuracy of the model. So typical challenges encountered then to take advantage of certain geometry topologies like thin walls or beam type structures for frames, that kind of thing. The tool that you need to use has to have that ability. And what we're really looking at doing here is creating smaller, more efficient models without compromising accuracy. So these are cases where solid element meshes can't really realistically represent all the modeling possibilities. So, we have a thin wall structure. You can fill it up with solid elements, of course, but you end up creating a huge model, and, it's sort of an order of magnitude even worse when you're looking at frame-type structures. So there may be cases where we need to depart from the solid geometry and solid elements and start to use two-dimensional or even one-dimensional element types. I mentioned just now more advanced types of analysis like dynamics and nonlinear are more numerically intensive, and actually, they can be iterative as well. So it's multiple solves, not just a single solve. Also, another point, when we get away from the solid geometry and using 2D and 1D elements, visualization, actually being able to see the model, becomes important, because if you look at just a model containing 1D elements, you want to be able to see it more than just a series of lines. You actually need to be able to visualize the actual underlying shape in order to make sure that it's oriented correctly and positioned correctly and what have you. So typical challenges then, the ability to take advantage of certain geometry topologies for finance modeling and creation, creating smaller models without compromising accuracy, so turning solid elements into two-dimensional or even perhaps one-dimensional elements if you're looking at frame-type structures, and just getting away from solid geometry, to create these small, efficient models. Some more advanced analyses types have to use different types of solver, different types of solution inside the solver, as I mentioned, which they're more numerically intensive anyway, so it really does make sense to build models which are accurate and efficient. And the final thing, of course, is visualization. So we're really looking at avoiding the creation of unwieldy solid models, which are time-consuming, and also take a long time to view the results as well, because you have a large model, you run it through a solution, it produces a lot of results data. So looking at the first thing then, mid-plane extraction. You have a thin-walled solid. It's very straightforward to extract the mid-plane of that, and once you have the mid-plane, you can mesh it with two-dimensional elements, and suddenly you move from a 3D model into a 2D model, and with no loss of accuracy, as the elements are very efficient. And if you look at a comparison of these two models here, you have a model which goes from 53,000 nodes down to 11,000, and you can see a much more efficient model to analyze, and produces a lot less data in terms of results. So, and without any compromise of accuracy. You can take it to another stage where you can look at frame type structures, and instead of creating a three-dimensional solid model of a frame, you can actually reduce it down to just a handful of beam models. Again, the beams are associated with the cross-section. This becomes an element property, and the cross-sections can be actually retrieved from libraries or can be user defined, or you can actually draw them and have the properties calculated automatically. So a very efficient way of modeling beam type structures, and also from the point of view of post-processing, produce a lot less data, but you can still access all the necessary data that you need to. So for beams, you can access shear force bending moment diagrams, and actually even get down to cross-section contours as well. Okay, so customer that makes good use of these beams is a company called Gusto MSC. It's a part of single buoy moorings. And you can see that the type of structures that they have to design the whole ship, the whole hull of a ship. Clearly, you can see in the quote there, it would be impossible to take a solid modeling approach to that. Obviously, a ship is a thin-walled structure, and you can get down to extracting these planes and creating a good mesh of 2D elements and 1D elements combined, and get a very accurate finite element model of a very large structure, which will analyze very efficiently. So the keys to success here was the use of FEMAP's plate and beam modeling and meshing. They mentioned the Windows environment here, and also the API, which I mentioned a bit later on. This is the application programming interface, another powerful aspect of the FEMAP program. And the results, potential hull problems using this approach, this modeling approach, could be found and eliminated very early in the design phase. Okay, let's take a look at another demo at this stage. This is a bracket type model. It's thin sheet type model, and we'll look at bringing CAD data into FEMAP. We'll extract the mid-plane, and we'll look at some of the geometry preparation tools I mentioned earlier ahead of meshing, just to align the model and make sure that we get good meshes in areas we think which are going to be problematic. So we'll see some of the geometry preparation around things like stress razors, like a couple of those holes there.
Welcome to the FEMAP model setup demonstration. In this demonstration, we'll see a CAD model of a bracket imported into FEMAP, the resulting solid converted to a mid-plane surface model, and some further geometry manipulation in preparation for meshing and creating a shell FE model. The CAD model provides a convenient starting point for finite element model creation, so it's important to be able to access this data easily and robustly. FEMAP is CAD neutral and can provide seamless geometry access to all major CAD systems, including CATIA and Pro Engineer. FEMAP is based on the industry standard Parasolid geometry engine, and also supports all of the main geometry formats for import and export. With the geometry of the bracket model now imported, we can see that it's a thin-walled solid. We'll exploit the model topology and create a surface model by extracting the mid-planes of the solid. This will allow us later to create a more efficient and accurate shell finite element model. In this example, we're finding all of the tangent surfaces on the exterior face of the model, and offsetting them to the center to get the mid-planes, a very quick and easy method of mid-plane extraction for sheet metal components. Now, with the model essentially composed of surfaces which will eventually be meshed into a shell finite element model, we can now perform some further modifications to the geometry. The intention of these modifications is to ensure that a high-quality mesh is produced in areas where high stresses are expected, such as holes and other stress razors. FEMAP provides a number of geometry modification tools to allow good meshes to be created around holes, such as the washer and pad shown in this demonstration. These tools use offset curves of the target entity to split up the surrounding geometry into regularly shaped surfaces. Also available are geometry splitters that can be used to split up other surrounding geometry entities to ensure that a regular and accurate finite element mesh will be generated in areas of the model that contain irregularly shaped surfaces. So these geometry modification tools can be used to help create regular meshes in areas of interest to ensure that.
Okay, so in the process of this webinar today, we've gone from, we're looking really at the process of going from the CAD model to the FE model, and we noted three typical obstacles that people encounter on the way. The first roadblock was, actually accessing CAD data, and we saw through the use of FEMAP that FEMAP can import CAD data reliably from a wide variety of sources. That roadblock was overcome. Once we have the CAD model read into the simulation environment, the next roadblock was actually turning it into something which can be used in terms of getting rid of unnecessary details and even problematic geometry that exists that can lead the mesher astray and create small elements which capture the detail which isn't really needed. So we've seen FEMAP has a lot of automatic and manual geometry preparation capabilities which can overcome that. And then the third roadblock is there are occasions where, particularly if you're considering moving into more advanced types of analysis, where we need to have the ability to perform geometry idealization to reduce the model size and depart from the solid CAD model itself. And FEMAP has a lot of very powerful capabilities and to do that, so it overcomes that third one. And overall, it allows us to, by removing all these roadblocks, it allows us to keep simulation to be as fast as possible, which is very important. We saw at the beginning that reducing design time is very important, and also having simulation respond fast enough so that it keeps in step with design is important as well. So it allows us to reduce the development time and speed time to market and maintain our design deadlines and so on. Okay, well, we've just seen FEMAP in, just just going from CAD to bringing in CAD and idealizing it. Of course, FEMAP does an awful lot more than that. It is a completely comprehensive modeling tool. Can solve complex engineering problems, produces high-quality solutions. It is window-based, so it's easy to use and easy to learn, and that increases productivity overall. As a pre- and post-processor, it is CAD independent that we've seen. It is also solver independent. We'll be talking about that in the next webinar. And it also, as I mentioned a couple of slides ago, it has this application programming interface which really allows, it turns it into a powerful integration platform for third-party solutions, basically, and can deal with other programs very effectively. Okay, so to find out more, you can go to the FEMAP website. Just type in femap.com, and it'll take you there. We also have a free trial available. This is a trial for 45 days. It's FEMAP with NX Nastran, and it's the full product, FEMAP with basic NX Nastran plus dynamics and optimization. And as I say, it's the full product for 45 days, so you can actually try it on your own data. I should also mention we have coming up in just under a month's time a FEMAP symposium, so if you want to find out more, it'd be a very good way of finding that. Finding out more about FEMAP, hearing some FEMAP case studies, and seeing how other people use FEMAP and other third-party solutions that can be added onto FEMAP. So the FEMAP Symposium's there. It's in Cincinnati on June the 25th and 26th. And with that, I think brings almost to the end. I should advertise the next two webinars. The next stage along the road through the simulation process is creating an FEA model. Once we've established that we've got the CAD data in, we can idealize it. The next stage is actually creating the FEA model, and that's what we'll be looking at in the next webinar. And that's in the 25th of June. And then a month after that, on the 23rd of July, we'll be looking at the next stage, which is once we've gone through analysis, actually looking at results and some of the roadblocks that can appear with post-processing. So that brings me to the end of the webinar today. I'll just move it on to one more slide and put this back onto the 45-day trial. And here you'll be able to access the website to access the 45-day trial if you'd like to. Okay, so Mike, I think we can open it up for Q&A now.
Yes, okay, that sounds good. Al, I'll let you and Chip take care of the Q&A. I did want to mention one thing. We had a problem with one of our PDF files on the site, and we are going to make that available for the replay. So everybody on this webcast will receive an email once the replay is available, and if you were unable to download that one case study from NOESIM, then you'll be able to get it on that replay. So let me go back to you, Al, on the handling the Q&A.
Okay, thanks, Mike. So let's see, one question that came in concerning importing CAD data. In particular to material properties, if you import a CAD model into FEMAP, will it bring the material properties in with it? So, Chip, can I hand over to you? Would you like to?
Sure. The direct CAD interfaces, particularly the solid edge interface, if material properties are assigned in the CAD model, we can import those material properties as well. It's primarily dependent on two things. One is, have the material properties been assigned in the CAD model, and secondly, what the direct CAD interface is. There's a few other questions that I noted. One was, will the software simulate water flow from a fire sprinkler system? FEMAP has a optional module called FEMAP Flow, which can do CFD-type problems. It's primarily targeted towards the electronics cooling applications, but it can handle different types of liquids and gases. So depending upon the type of system you're trying to model, there is that solution with the FEMAP Flow module. There was another interesting question having to do with how much validation or testing do you recommend to verify the accuracy of the FEA model in simulation? And this is really kind of a broad answer. It really depends upon whether you're doing part or system level simulation. I've seen companies do a single FEA analysis in to validate the structure before the actual first production model has been produced. I've also seen, particularly in aerospace, where they do what they call, they'll do validation. Will actually look at the FEA model and correlate the results from the FEA model into the physical test, and then tune the FEA model to match the physical test and go from there. So there's really a lot of, there's not a single answer to this. It depends on the product complexity and the use cases, and also what type of regulatory factors are involved in producing the product. Another question, will there be a talk about CFD in the future? We don't really have a particular webinar planned on this. However, what I'll do is I'll make a note of this. I believe we've had some webinars in the past about the FEMAP flow and the FEMAP thermal products. So what I'll do is I have the email address, and I'll see if I can find the link to the replay of that FEMAP flow webinar. So let's see if we have any other questions. No, I don't think so. There was one question, and Al, maybe you could answer this. One question was, is there a copy of the actual slides available for this?
I guess.
Hey, Al, yes, there should be a way to download a PDF of the slides right in the resource link on your screen. So they are available for download currently. And you'd be able to download them if you came back to the replay. Okay, is that it on the Q&A?
I guess I think so. I can't see it.
Okay. Well, if we missed your question, we'll get back to you via email directly. And thanks for joining. And you'll get an email in a couple of days on the replay. So please forward this to anybody else you think might be interested in doing this, or you can view it again. And with that, we'll say have a great rest of the week. Thank you.